Recording. So just to recap last week. So on Friday, we had a very sweet day. So on Friday, we showed this series, the harmonic series, which looks like this. Written in summation notation, it looks like this. And so it's 1 plus a half plus a third plus a fourth. So we actually showed this creature diverges. And we did it in a very, what I find to be creative way. We compared it to an integral that we know diverges. That's what we did, and that's pretty. That's you know, that in and of itself, that's a pretty cool thing as a theme. That is, when we want to get information about one entity, we can often compare it to a known entity. We've done that already in this class on the midterm, or excuse me, on the homework where we had that. No, it was the midterm problem with the integral e to the negative x squared. And that is a theme in advanced math and science that happens all the time. So let me repeat this, because if any of you are serious about learning this, this is a good, important thing. The big theme with showing that diverges was to take this sum and somehow compare it to something we know diverges. So we actually showed that this sum had to be bigger than an integral that diverged. So that was pretty fascinating, if you ask me. And it's a theme we're going to come back to. It's also worth pointing out that in many ways, people found, and it was when it was first discovered that this series diverged, it was, to many of the mathematicians at the time, they were kind of shocked. It seems, at least intuitively, we think this thing might converge because, again, it looks like the other ones that converged, 1 plus a half plus a third, but it doesn't. So the question that this sparks then, what properties do we expect? What's happening? What's happening? What properties do we expect a convergent series to have? So another way of saying that is to do the following. That is, if we know, take a generic series, let's call it the terms in the series a sub k. So let's take a sub 1 plus a sub 2 plus a sub 3. If we know this thing converges, what conclusions can we make? So this is something I would encourage you to think about in your, if you, again, I can't force you to want to care about any of this, and I don't expect all of you to. Some of you I know are just going to go through the motions and get through the class. That's all right. I don't begrudge you for that. But if you are someone who wants to learn this stuff and have a deeper understanding of it, then I highly encourage you spend some time thinking about this. What can you say about this generic series? What can we say about a sub 1, a sub 2, etc., if we know that the series converges? So say that again. You said something? Well, okay, but no. You're thinking you still have your you still have in your head the ratio, excuse me, the geometric series. But I'm not saying anything about these numbers. Who knows? It turns out we're going to be able to make lots of different sort of statements about how a series behaves when we have certain assumptions. But right now, the only assumption I'm making is I am making the assumption that this series converges. So let's think about this, and this will be our one scary thing. Well, everything's kind of scary, but this will be our one sort of deeper sort of work today. So let's assume that this series, which we wrote down, and remember, what does this mean by definition? By definition, it means this. Let's assume that it converges to some number S. We'll call it S for sum. It's the sum. So remember, we gave this guy a name. So let's set S sub n equal to this guy. A sub 1 plus A sub 2 plus A sub 3. And then what we can do is we can be very specific with how we write this out. So let n be some number. I don't care what it is. Maybe it's 29, maybe it's 1,000, maybe it's 452 million. What you need to note is, and someone actually pointed this out last week, and it's worth noting, if I take this guy, these guys are S sub 2, and then what are the first three? These are S sub 3, etc. So in general, all the way over to here is S sub n minus 1. And so what you can conclude, albeit might be a little overwhelming for the beginners, is you can conclude that S sub n take away S sub n minus 1 equals A sub n. I guess I should be more specific with my n's. Let me use, I got to be consistent. I've been using uppercase n, so let me fix that. This is n minus 2. This is A sub n minus 1, and this is A sub n. And so this should be an n. Yes?
Is that A sub n included in that S n minus 1?
What do you mean, here? No, it's just up to here. It's not. Because this is the first n minus 1 term. So the question, so this just goes up to this guy. So here, maybe I'll even be more specific in the next line. I won't go so quick. So if I look at what the pink thing's telling me, I have S sub n equals S evaluated at n minus 1 plus A sub n, or if you just rearrange it, S sub n minus S sub n minus 1 is equal to A sub n. So this is the operative equation. So, okay, so what does this mean? Well, remember, by definition, this is a partial sum. This is a partial sum. And we know that if we take the limit of the partial sums, that is this sum of the series, if it converges. But we're assuming it converges. So if I take the limit of the left-hand side of here, it has to equal the limit of the right-hand side. That is what has to happen. Now, if the series converges, that means this and this have to converge to the same thing. So what can we conclude? We can conclude the following. Therefore, the limit as n goes to infinity of S sub n minus the limit as n goes to infinity of S sub n minus 1 has to equal the limit as n goes to infinity of A sub n. But the left-hand side is just S minus S because the limit is S. That's what we assumed. We assumed that. And then, of course, that means that 0 is equal to this limit. So this is actually very big news. It tells us something very important about terms of a convergent series. So what this tells us in English is the following. If a series converges, then the terms must be approaching 0. That sounds annoying.
Yeah.
You hear it too? Is that why you're looking? Like, what is happening?
It just got louder.
I know. It's like it's trying to suck me out of here. We have technical difficulties. The fan or the vent in the ceiling is whistling in my ears. So here's what to make of this. This is an amazing fact because it's sort of what that means. Sorry about that. My head's about to explode. Let me fix this because that's on my nerves. And by the way, I understand that for most of us at this level, these subscripts and limits, this is very overwhelming. And don't expect to, I mean, if you really want to learn this, it's going to take some time to really think about what each of these symbols means. So here's the conclusion, though. The conclusion. If this series converges, the limit of the terms must go to 0. So what does this tell us? It actually tells us something, but we have to think of it in a different perspective for it to really be useful to us. So if any of you have ever studied what we call logic, you'll know that there's equivalent ways to say certain statements. And so there's an equivalent way of writing this. And the fancy word for it is called contrapositive. I don't know if you know what that means, but basically what it means is the following. So this is logically the same thing, or logically equivalent to what we call the divergence test. If the terms don't go to zero, so if the terms do not go to zero, what you can conclude is the series diverges. So this is we call it the divergence test because it tells you right away if a series diverges. So let's do some examples.
Can you go back one?
Sure. Does anybody have a comment or question? Good? So even if you're overwhelmed by this argument that we just spent pages 3 and 4 on, actually 2, 3, and 4, the result, the sort of the reward from it, what we get from it is this. It gives us a very simple way to tell if something diverges, not converges, but diverges. So this test is useful to verify a series diverges. So let's look at some examples of how we can use it real quick. So while we're doing this, don't forget the big issue here. What's the big issue? The issue is, I pointed out to this numerous times now. A series in general is not easy to analyze. We get sort of this misconception that they all have some simple formula. There is only one class of series that have that simple formula. That is the geometric series. Other series do not have a simple formula. So the best we can do is determine if it converges or diverges. And so what we're setting up for is we're going to develop a series, pardon the pun, of tests that help us understand when a series converges or diverges. So let's look at a couple examples here and how we use this test to make some sort of deductions about series. So let's take this series. Let's take the series of K. K goes from 1 to infinity. What does this series look like? This is 1 plus 2 plus 3 hopefully we don't expect that this thing converges. But even if we thought for a second it might, this guy diverges. Why? Because the limit of the terms doesn't go to 0. What is the limit is k goes to infinity of k? Well, this is equal to infinity, which is clearly not 0. The terms in that series are not going to 0. They're getting larger and larger. Let's look at another one. How about one that it might look like it converges? How about 2k over 3k plus 1? K goes from 1 to infinity. What does this guy look like? Well, this is 2 fourths plus 4 sevenths plus 6 tenths plus 8 thirteenths. This guy also diverges. Once again, why? Because the limit of the terms, if I take the terms and ask what is their limit, the limit of this expression is 2/3, and last time I checked, 2/3 is not 0. Yes.
I was just curious, is it possible if a series starts with infinity going to 1?
Say that again?
K starts with infinity going to 1. Like backward.
I don't know what you mean by that.
Like instead of 1 over there, you put infinity, and then where infinity is, you put 1.
You mean you're asking to put a 1 here and an infinity down here? No. That doesn't, think about that. It doesn't make sense. Now, you could put any number down here that you want, but it doesn't make sense to reverse, because by definition, how are we defining this? This thing means there's a first term, a second term, a third term, a fourth term, right? Yeah, so the question was, can we put infinity down here? Well, that wouldn't make any sense, because the reason notice these numbers, by the way, have to be positive integers. Because, again, you're thinking of this as the first term, the second term, the third term, the fourth term, etc. Does that make sense? Now, that being said, it doesn't matter if I start at 0 or 5, because it's still, you can say, okay, well, we're just going to ignore the first 4 terms. So this is the 5th term, 6th term, 7th term. What we're really asking, and what these series are doing, is they're studying what's happening far out. What's happening when the numbers become large, right? So these series, this one, intuitively, we're going to say there's no way this converges. There's no way that if I keep adding up positive numbers, I get a finite value. This one might not be so obvious. You might think that these guys add up to something. Turns out they don't. Let's do one more example.
And how about if you subtract instead of adding? What is that called?
Well,
Addition is called partial sum, right?
yeah.
So,
Well, okay, so you're saying subtracting the terms?
Yeah.
Well, I mean, there's plenty of times we're going to subtract. Here, look at this example. Maybe this will help. It just so happens that all these terms are positive, but they don't have to be. So, for example, if I look at, here's one that might be of interest. Let's take -1 and raise it to the k plus 1 power. So what is this equal to? When k is 1, you get positive 1. Then when k is 2, you get minus 1, plus 1, minus 1, plus 1, minus 1. And this goes on forever and ever. This guy diverges. Why does it diverge? Because the terms, this limit, does not exist. There's no limit there. That just balances between -1 and 1 forever and ever. There's no limit.
What do you do with the -2? There's different numbers, right?
Say that again?
If you put a -2 over there, instead of -1.
If I put a -1, I still don't know what you mean.
If
Where
you put a -2
Here?
over 1 on top over there.
up here?
No. Yeah, there. -2
If I-
instead of 1.
If I put a -2 here?
Yeah.
Okay, so let's look at that one. It's the same thing, but the numbers, it's still going to diverge. So that's a good question. So the question was, what happens if this is -2 to the k plus 1? Well, what's going to happen here? The first term is -2 squared, so that's +2, right? The next term is -2 to the third power, right? So that's -8. And then when it's 3, you're going to get +16, right? And then -32, and then +64, and then -128. Is that what it is?
So if you're subtracting one from that.
Well, it's just that this pattern is not going anywhere, right? Right? This is going to diverge as well. And again, okay, another way to think about this is if you spent the rest of your life doing this pattern, you're never going to go anywhere.
It's like the like 3 steps forward, 1 step back.
Sort of, right. And the same reason applies to why this one diverges, because this limit does not equal 0. The only way for a series to converge is if its terms are getting small. These numbers are not getting small. In fact, they're getting bigger. These terms aren't getting small. They're bouncing between 1 and -1. These terms aren't getting small. In fact, these terms are getting closer and closer to 2/3. They're not getting close to 0. These guys are getting bigger. Now, if you compare to our geometric series, by default, the terms are getting smaller and smaller. Take a number less than 1 and raise it to a large power. It is very close to 0. It's getting closer and closer to 0. Does anybody have a question about this? Now, here's something to ponder. So here is an interesting situation. This series, the harmonic series, 1 over k, which is 1 plus a half, plus a third, plus a fourth, etc. This guy diverges even though the terms go to 0. So even though these terms are getting smaller, it's still not enough to guarantee convergence. So this divergence test is a one-way street. It can only tell you when something diverges. It can never tell you when something does converge. So this is, again, these ideas, this is very, very difficult to sort of absorb as when you're a beginner. And that's what you guys are in calculus 2. I know most people say this is calculus 2. That's just crazy. You're so, calculus is like the most basic math. I mean, I hate saying it. It sounds like a jerk thing to say, but this is not, if you're studying at the university level, calculus is the lowest math there is, right? At least in science. It's basic math. Now, I don't say that to be insulting. The fact of the matter is it's basic in the sense that it's what you study your first, the first subject you study, but it's not easy to learn this stuff. This stuff is difficult to learn. And you guys are beginners. And it's really hard to be a beginner where you don't have that much exposure to this to understand it. And look, I know what it's like. I sat in a class just like this many years ago, and I was clueless like you are. That's part of it. Does anybody have a comment or a question? So I don't just sympathize with you guys. I empathize. I know what it feels like to sit there and say, what in the hell is on the board? What's that? You just go, well, nothing wrong with that either. Just sit there very pensive and like, if you make like faces like every 30 seconds, it's like, I can't really see your faces because of the mask. Man, what a time to be alive. Have we figured out the Roni yet? I wonder what's going to happen. There was all those people that thought the Roni is going to end immediately after the election. So we'll know who was right or wrong next Tuesday, right? Oh, shit. Well, there are those people. I saw these people the other day. They were complaining because I guess Biden must have tweeted something last year about the current administration not knowing how to handle pandemics. And that was like in the October of last year. So then all these crazy right-wing people are saying now that Democrats, Biden, and they created this to win the election. So we'll see what happens. It is Tuesday, right? Election day. Man, a week from today, hopefully all this chaos will end. I'm sick of my phone rings. Every time it rings, it's a different place on the planet that's calling me. I don't answer because I know what they're going to do. They're telling me to vote for people.
So many phones.
Yeah. I like this morning, it was like Florida was calling me. Yesterday, like Texas was calling me. I can't imagine what they're going to tell me. It's either them or it's those people trying to get you. They think you're the IRS. They're trying to like scam you out of something, right?
Yeah.
They take advantage of old people. Don't be that person.
Don't get old.
What's that?
Don't get old.
Well, no, I feel bad. I'm saying don't be the person that takes advantage of old people. No, you got to get old. That beats the alternative, right? That's what my father-in-law says. Okay, so why do we care about all this? Well, it's time to actually write down what I've been saying. So we have to sort of remind you of, our job for many reasons, the least of which is this is a math class and this is the topic we're studying. And that is we want to study series. We want to know how a series, what are its properties, how does it behave? So given a series, we'll just put a generic one down, a sub 1, a sub 2, a sub 3, etc. We'd like to know, first off, does it converge or diverge? It can't be both. It's one or the other. And then if it converges, what is the sum? And of course, I'm going to put the word sum in quotations because remember, we're not adding up things infinitely. We're actually, this is a limit. And I wish it's, and I hate saying that, and I get so like annoyed at myself because I know how hard it is for you to even understand what I'm saying. Like, what the hell does he keep talking about? It's a limit, right? That's exactly what you're thinking, right? That's okay. You probably go home and fire darts at like a picture of me on the wall or whatever you're like. But how do you know? I practiced this lecture last night, and I get all the crumb snatchers, Lydia and Ricky, and then all their stuffed animals, and we go in the bedroom and we practice this lecture. Lydia raises her hand and says, "Oh, that's easy, Daddy." I said, "Yes." You should see the math they're doing in kindergarten. 9s and 10s. That's what they're doing right now. How many is there? Is there 9? Is it more than 9? Is it less than 9? More than 10? So way to go, kids. So we know, so for geometric series, what does a geometric series look like? A geometric series looks like this. It's a number raised to the index. We know this is quote unquote easy. But in general, it's not. So again, we got lots of letters floating around. I don't know what the answer is to help you with that. You just got to keep pushing forward and saying, I know I will not let the letters kill me. I will not let the letters kill me. Maybe you guys should say that before you go to sleep at night when you wake up. The letters will not kill me. The letters will not kill me. No one has ever been in the obituary and said death due to staring at a whiteboard. It's never happened. It's never been death because I did calculus. Well, that's not true because lots of people use calculus to build weapons and then people die. Yeah, but that's bad. We shouldn't discuss that. But don't be afraid of the letters and the symbols. So why do we classify things? Well, we classify things so we know how we can handle them. So if you're geometric, if you fit that classification, we know that there's a very simple way to study you. But if you're not geometric, then it's not so straightforward. And so what we do then is we develop a bunch of tests. So maybe I shouldn't say that. So to help study series in general, we use tests. And we have 2 of them already. So we have already showed you 2, although we showed you what's called the integral test and the divergence test. So how did we use the integral test? Well, where did this show up? Well, we actually proved the divergence test. And the integral test is the proof of this is similar to our proof that the harmonic series diverges. So we're not going to do the proof because it'd be redundant, because no one's going to ask you to prove these in a Calculus 2 class. They're going to ask you to use them. So we'll do a couple of examples of how we can use the integral test. And we'll do that in 30 seconds once you guys ask any questions. I really hate that we're like hybrid, because we can't do the typical shenanigans of talking about life and all that fun stuff we normally do. So you never had class with me. That's why you don't get, Emily, you don't get this fun. You guys have no much fun you're missing out on. I'd be dancing in the room right now. We'd be looking at Facebook pictures or like reading weird things. I already gave you an extra credit of watching a movie, right? I'm trying to, I sound like you guys, poor English. You got anything you want to say? Questions? No? You sure? Add to the excitement. Could talk about life. I was supposed to be going to Florida this weekend. That ain't happening. Thanks a lot, Roni. I know. I'm supposed to go to Florida in September, and although that I was supposed to go to Disney in September, so that's the Roni actually probably saved me $10,000, right? Because taking a family to Disney World ain't cheap. Yeah. All right. My back hurts. It's tough carrying you guys all through the calculus. All right. Let's look at some examples. It's so funny. I literally just checked my phone to see what time it is. I have 2 computer monitors in front of me. I'm gonna watch that. Let's see what my resting heart rate is. My heart rate, I can't believe it. It said I'm like my resting heart rate today is 51 beats per minute. That's
really low.
That is awesome. You know what that means? I Googled it. It says high level athletes have resting heart rates like that. I knew I was special.
You are special.
I can't believe I bought this phone. Materialism is a hell of a thing. It really is, isn't it? First world problems. I stood under clean water for 20 minutes this morning. I got a computer on my wrist, one in my hand. My car, I don't even know. This thing don't even have a key on it. I still don't know how that works. Like how? Well, I guess I shouldn't say I know how that part works, but like how? It's very strange. Like there's like a thing on my car, but it only knows it's me. I don't know how it does it. It's very strange. You know the coolest thing? Talk about first world awesomeness. Like there's multiple things of these for my car. So like, and then it's all memorized. So whenever I open it with this one, it goes and puts all the things where I like them, like my seat and the steering wheel and the mirrors, right? Isn't that great? This is what I'm saying. Thank God the nerds figured that stuff out. Can you imagine having to wind your windows down?
Imagine being that poor.
Hey, when I grew up, listen, my dad was infamous for buying hoopties. That's what we call him. He would buy the cheapest car he could find. He would like use staple guns to keep the ceiling from falling down. My dad did not. He is against spending money on material things. He's against it. So I, on the other hand, am the opposite. When I was a kid, my mom would lie to my dad when I would get like shoes and stuff. We'd have to hide the receipts. So my dad didn't know, like, because I would buy like expensive shoes and, when I was in like 6th grade, there was these jeans. Well, they still sell Guess jeans now, but Guess jeans was real popular. And then there was these sweatshirts called IOUs, which were like a status symbol back in those days. And I'd have my mom buy them from me. We weren't allowed to tell my dad. I was like, way to teach me how to lie, Mom. I mean, hide the receipt. Not Dad. Of course, he probably knew anyhow. You need how many pair of shoes? I said, Dad, I need shoes for basketball. I need them for school. I need play shoes. This is what you need. First world problems. Although I shouldn't joke about it. Like, there are so many different levels of like, oh, we ain't getting in it. Let's get back to math. Examples. We're getting out of control. Getting out of control. All right. Let's look at an example of how we might do this. So here are some integral test examples. Now you might say, well, you didn't write down the integral test. I don't want to write it down. It's scary looking. Let's look at examples. It's in your book anyhow. You could Google it. Let's just show you how to use it. So the first one we'll do is a very basic one. Does 1 over k squared converge? So this is 1 plus. When I plug in 2, I get 1/4. When I plug in 3, I get 1/9. That is an ugly. When I plug in 4, I get 1/16. When I plug in 5, I get 1/25, etc., etc., etc. Does this guy converge? So this is not geometric, so that's not going to help. It passes the divergence test, so that doesn't help. It passes because the terms are going to 0, so it might converge. We don't know for sure, but we know it doesn't. We know it could converge. So we next go to what we call the integral test, and what we say is we recognize that this sum is connected to the Riemann sum of an integral. That's what we recognize, and so. And if you don't see it, draw a picture like we did on Friday. But you don't need to draw a picture, but you could. So the integral test says to study this integral, the integral from 1 to infinity of 1 over x squared dx. And again, I can't emphasize this enough. If you're not, you have two options here. You can just trust me and say that, study this, or you can draw the picture and see how this integral is connected to that sum. We did it once. We drew the picture for a similar problem on Friday, but the same idea holds. So we study this. We compute. If we want to study this integral, we have to take the limit as, say, t goes to infinity of 1 to t of, we'll write this as x to the negative 2 dx. Which is negative 1 over x, evaluated from 1 to t. You integrate it. And that's the limit as t goes to infinity of negative 1 over t plus 1. And of course, this thing equals 0 plus 1, which is 1. And what is the conclusion? The conclusion becomes, since the integral converges, the series diverges. Does anybody have a question about this? So why did I use the integral 1 over x squared? Well, look at the series. The series is 1 over k squared. If this were 1 over k to the 5th, I might think to integrate 1 over x to the 5th. And I should point that out, actually. So it's worth noting this because these series turn out to be useful. So a similar argument proves this series, 1 over k cubed, 1 over k to the 4th, etc., all converge. In fact, and this is what you really need to remember, in fact, this series, the series 1 over k raised to the power p, which is equal to 1 plus 1 over 2 to the power p, plus 1 over 3 to the power p, plus 1 over 4 to the power p. This guy converges when p is any number greater than 1. And then the series diverges when p is less than or equal to 1. So these guys are given a special name. They're called p-series because they're very easy to tell. You just look at them. They either converge or diverge. Converge or diverge. All you do is you look at this. Now, what's important to understand, and this is difficult, again, for beginners, notice the index is k. So this is the index. It's going to be 1, 2, 3, 4. This exponent is not changing. It's a fixed number. Here it's 3. Here it's 4. In the previous page, it was 2. So we call these p-series. So we call this thing a p-series. So it's worth noting. So let's look at a couple examples. One over k to the 3/2 converges. Write that a little cleaner. Why does it converge? It converges because p, which is 3/2, is greater than 1. However, if I take 1 over the square root of k, this guy diverges because p, which is 1/2 here, is less than 1. So this is why are we giving this series a name? We give this a name because they're easy to recognize. And again, I use the word easy in quotations, relatively speaking. To someone who's trained, they are easy to recognize. In Calculus 2, today, they're not that easy for you to recognize. But much like geometric series, you should, sooner than later, be able to recognize a p-series and a geometric series. And so it's nice to be able to recognize them because you can use them. And you might imagine, I said earlier, there's a theme about when you want to get information about a new thing, you compare it to something you already understand. Well, if P series and geometric series are easy to understand, maybe, just maybe, when we come across new things that aren't obvious, we can compare them and get information when we compare them with things like P series, and we will do that. Again, that's a very, very common theme, and that's not just in math, guys. You know this. I mean, think about what we do in science, chemistry. You know, we break everything down to the elements, and we think about gaining information that way. You know, what is water? It's H2O. We learn new things by examining old things. Another way of saying that is when we come across new things we don't understand, we think about simplifying them, and we wonder if what we already know about the simpler things can help us understand the new things. You know, the first boat that ever sailed the ocean wasn't the Titanic or some big cruise ship, right? I mean, I use this stupid, you know, metaphor all the time, or analogy, I don't know what you call it. But one day someone was walking along a creek and they said, oh, there's a tree floating in the water. Ain't that something? Let's tie a couple of these together and now we got a raft, right? And then it wasn't the next day that we had cruise ships. You know, these things have to slowly develop. And that's no different than when you're learning calculus. You have to learn these things and one step at a time, and understand that understanding the new stuff often comes down to thinking about the stuff you already know. How can you use previously known information to learn new things? But anyhow, okay, does anybody have a question about this? So we have two tests, and there's actually more than, you know. So, by the way, notice the harmonic series is a P series with P equals 1. So what is that? That's just 1 plus a half plus a third plus a fourth, etc. And we know that diverges. So another useful test which is the same theme as the integral test. We're comparing unknown with known. This one's actually more explicit. It's actually called the comparison test. So let me write this down again. I can't say this enough. Theme. We compare unknown with the known. So let's illustrate it with a example. Does 1 over k squared plus 2 converge? Actually, I always like to write the first few terms out. I think that's useful for your brains. So I'll do that. It's good practice. What's the first term? The first term is 1/3. The second term is 1/6. The next term, when k is 3, you get 11. When k is 4, you get 15. Does this guy converge? Now, we could go and try to study this directly, but we can also get a little bit use. So here's what I'd like to think about. Let's look at the partial sums, and let's compare them with something else. All right, so here's what I'm thinking about, at least intuitively. Let's note the following. The sum, k goes from 1 to, I'm going to stop at some n. So let's, what was our expression? If you remember, it's k, 1 over k squared plus 2. What is this equal to? This is equal to, we already know when k is 1, you get 1/3. We wrote this down previously. When k is 2, you get 1/6. When k is 3, you get 1/11. And then this pattern continues all the way up to, what happens when, you know, I guess we could just write the last two. The second to last one looks like this. And then the very last one looks like this. So n is some positive number. Maybe n is 10 or positive integer. Maybe it's 300. Maybe it's 50. Actually, for fun, let's do it this way. Let's do it this way. I'll make it even, hopefully a little easier to understand. Let's put a specific number there. Let's say 25. I don't know why I picked that up. So this would be this would be 24 squared plus 2, and this would be 25 squared plus 2. So what I'd like you to note, though, is that I'm going to try to compare this with something I understand. In particular, I'm going to write this creature down. And what is this guy? This is when k is 1, you get 1. When k is 2, you get 1/4. When k is 3, you get 1/9. What happens when k is 24? You get 1 over 24 squared. And then when k is 25, you get 1 over 25 squared. Now, what I want to notice is I want you to notice that if you line up the terms, the corresponding terms, notice this guy right here is less than 1. Is 1/3 less than 1? Yes. Is 1/6 less than the 4th? Yes. So this guy is less than this. This guy is less than that. 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 So in general, 1 over k squared plus 2 is less than 1 over k squared And this sum has to be less than this sum. And then, of course, if you take the limit, and what you get is you get that the series converges. So we got that it converged by comparing it with something that we already knew converged. Now, do you have to do this every time? No. The purpose of me doing this example was to illustrate the general theme. If you can show that the term in one series is less than the terms in another series where that series converges, then you can guarantee convergence. So this idea can be summarized as follows. So this is called the comparison test. Suppose 0 is less than or equal to a sub k is less than or equal to b sub k for each k. There are two options. If b sub k converges, then so does the a sub k. And the other option is if a sub k diverges, then we can conclude b sub k diverges.
So they went to, so one converges, then the other one.
Well, only if it has to fit this assumption. Every term in B has to be bigger than its corresponding term in A. So if you go to the previous example, that's what I was trying to illustrate. This would be your a sub k, your a sub 1, a sub 2, a sub 3, and they are all smaller than b sub 1, b sub 2. So a sub 1 is smaller than b sub 1. A sub 2 is smaller than b sub 2. A sub 3 is smaller than b sub 3. So in general, this number is always less than this number. So really, if I wanted to use the comparison test, I didn't have to write out the purple. I could just have said this is true because it's an obvious algebraic fact. This number right here has a larger denominator than this number, so this has to be less than this. And a close relative before we go is called the limit comparison test. So suppose a sub n, or excuse me, a sub k is greater than or equal to 0, and b sub k is greater than or equal to 0 for each k. If the limit as k goes to infinity of a sub k over b sub k is greater than 0, but not infinity, then a sub k and b sub k both converge or diverge. So if you know one diverges and you take this limit, then you can say that you can guarantee the other one diverges, and vice versa. So if you know information on one of them, you can get information on the other. That is the theme of today. Integral test, comparison test. If you know information about one, you can get information about a new guy. All right. So what we'll do is we'll give you an assignment that asks you to practice all these things. And again, oftentimes you're not sure, other than through experience, which test to use and when. So that's why we practice. Okay, does anybody have any comments, questions, anything you want to say? All right, well then we'll wrap it up, and I will see you all Thursday. Thank you very much. Uh-oh, someone's chatting it up. What do they want to say? It's good. I can't wait to see what you wrote about it. Yeah, I got to post that extra credit online.
I was gonna say, I didn't see that.
I know I didn't. I sent an email about it, but I didn't put it on Canvas yet. I'll do that. Relax. All right, gang. Thank you very much. See you later. Take care.